In this video, we're going to look at reasons why the Newton-Raphson method sometimes fails, and we're going to do it by means of the example that is shown here. The function is a rather complex one, and so the graph has been provided. f of x is equal to 6x plus 2 over x plus ln x minus 10. There are two roots to the equation f of x is equal to 0, alpha 1 and alpha 2, and they're shown also on the graph. And we're going to be using Newton-Raphson and trying to find out why for the values 0.4, 0.5 and 0.6 the Newton-Raphson method fails to find the value of alpha 1. I'm using this example to show reasons for the failure of Newton-Raphson, rather than immediately showing you the situations in which failure occurs, because it's always best to do a little bit of analysis to support the conclusions that you have regarding the failure of any of these numerical methods. So we'll begin by differentiating f of x so that we can determine what f dashed of x will be for use with our values 0.4, 5 and 6. So f dashed of x will be 6, the derivative of 6x, minus 2 over x squared, the derivative of 2x to the minus 1. The derivative of ln x is 1 over x, and 10, of course, has nothing by way of derivative. And so that's what we're going to be using in our use of Newton-Raphson with our starting values. Our first value to try then is 0.4. So we're going to put that into the Newton-Raphson relationship so that our next value is 0.4 minus, and then on top f of x with x substituted with 0.4 throughout, over f dash of x, where x is again substituted for 0.4. And when we evaluate that, we find that x1 is equal to negative 0.47907. Well, if you now look at the graph, you can perhaps see what's going on. If we draw the tangent roughly where 0.4 is, we end up with a value x1 which is to the left of the y-axis. Well, the y-axis for this curve is an asymptote, and there is no part of the graph on that side of the y-axis, and so we can't proceed any further. The reason for this is that f of x contains a natural log term, ln of x, and ln x is undefined for negative values of x. So we're in a position now to give our explanation as to why the method fails. F of x is undefined for any values of x which are negative, and so the method fails. And that then brings us then to the first reason for failure with Newton-Raphson, and that is it will fail if it finds a value that is outside the domain of f of x. Remember that the domain are all the valid values of x for which the function exists. So we come to our second starting value, which is 0.5. And if we proceed as before and begin to enter this into the Newton-Raphson relationship, we will get that x1 is equal to, and you'll see that I've simply replaced all the 0.4s that we had in part A with 0.5. But when you enter that into your calculator, you'll get a maths error. So what's going on here? Well, 0.5 is at the very bottom of our graph, and so we have a horizontal line for a tangent, and therefore it simply never intersects with the x-axis, and so that's why it's undefined. So we can give as our reason for failure that f dashed of x is equal to 0 when x is equal to 0.5, and that causes the method to fail. And of course we can now say more generally then regarding Newton-Raphson that it fails if a stationary point is used either as a starting value or if the method itself happens to land on a stationary point, which is admittedly very unlikely. It's worth saying then that having some knowledge of the shape of the curve and solving the equation f dashed of x is equal to 0 to find the stationary points are just good practice in helping to establish viable starting points when you're using Newton-Raphson. And so we come to part C, where our starting value is now 0.6. And just as before, we enter that into the Newton-Raphson relationship. So that's what it would look like. And when we press the equals button, we get the value 2.2946. And so far, so good. And so we proceed again and we carry on, and we get a sequence of values that homes in quickly to 1.3709. And it may be that you have already guessed as to what would happen with this third starting value. And this is regarded as a fail, just in the sense that it homed in on a different route than the one we really wanted to find. And so this finds the other solution alpha 2 rather than alpha 1, which was our intended target. And so we can say that Newton-Raphson may find another solution than intended if you start on the wrong side of a stationary point. In this case, the tangent to the curve goes in the other direction. That gives us a new starting value, and the tangent to that point goes down towards alpha 2. And that's what we've experienced as the numbers unfolded in the repeated iterations. I want to conclude this video with just a few observations about the interval in which a solution can be found, and some comments about starting values. So the first thing to say is that for this function, x must be greater than 0. Otherwise, with that natural logarithmic element, it's going to be undefined. And that, of course, has some consequences. When we're trying to find an interval in which a solution is found, we have to try some values, and the lower limit, a, in the interval must be between 0, not including 0, up to, but not including, the actual root alpha 1, because on that side of alpha 1, y is positive, and then the upper limit for our interval would need to be a little bigger than alpha 1. Our question had 3 possible starting values, and it would be true to say that the change of sign method would confirm that there is a solution that exists in any of these intervals, either from a, as discussed, up to 0.4, or from a to 0.5, or a to 0.6. And it's really important to realize that although we know that there is a solution that exists within that interval, or those 3 intervals, we can't simply use the boundary values as starting values for Newton-Raphson without a real appreciation of the shape of the curve and the position of any stationary points. From the work that we've already done, we now know that if you take a starting value of 0.4, Newton-Raphson is going to fail. But there is a limiting value. There is a tangent that will pass through the origin, and the x value of that point will be the upper limit for starting values that will converge on the root alpha 1. We'll call that b. it might be a good exercise for you to try and find out what that value of b is in our case. My advice though would be to wait until you've seen the final sequence of videos on fixed point iteration, as that might prove an easier method to use in this instance. How can I select a starting value then to be absolutely certain of finding the root, the solution that I want to find? Well, if I want to find alpha 1, my starting value x0 needs to be between a, the lower limit of the interval in which I found a change of sign, and b, this value that I've just been speaking about. Now I know, because we can see the graph, that we could actually probably go lower than the value of a, but it's unsafe to go lower or higher than the boundaries of the interval that you found the change of signs for, in case there is some unexpected behaviour of your function. It's a little simpler with finding alpha 2. Once I go beyond the stationary point at x is equal to 0.5, any value that I choose will eventually home in on the second solution, alpha 2.